So, could you introduce yourself?
My name is Masaki Hori of the Max Planck Institute for Quantum Optics and also the University of Tokyo of Germany and Japan.
So what is the purpose of ASACUSA experiment?
Here we measure the mass of the antiproton relative to the mass of the electron. This is called the antiproton to electron mass ratio. And what we do is we synthesize atoms that contain antimatter. This is atoms that are half matter and half antimatter. We produce them in this experimental target. We then shine laser beams on these atoms and measure their transition frequencies very precisely. What we do is we measure the color of these antimatter atoms very precisely. And then from this we can determine the mass of these antiprotons.
Why it is so important for the antimatter experiments to measure the difference between proton and antiproton?
Yes, so the universe has this duality between matter and antimatter. Duality means that for some reason, for every matter particle, there's always a corresponding antimatter particle. And we believe that the universe has a fundamental symmetry, wherein the masses of these particle and antimatter particle are exactly the same. And this is a belief that we have of the standard model of particle physics. And here we have to verify whether this fundamental symmetry is correct or not. In fact, this symmetry is so fundamental in our understanding of nature that if it's broken, then we really have to rethink all our theories of particle physics.
And what are the next steps for your experiment?
Oh, yes, so far we are trying to, we've measured the mass of the antiproton to 1 part in 10 to the 9. Okay? And in the next step, we believe we can measure the mass of the antiproton more precisely than for the proton. In that sense, we would know the properties of antiparticles, antimatter particles, better than for normal particles. And this would allow us to probe deeper into how the universe is and how these matter and antimatter particles behave. So, my colleague there has a normal helium bottle. And this is the same type of bottle that you use for balloons and so on. Okay? Nothing is special about this bottle. It's normal helium. We put this helium into this chamber. Inside the chamber, we can cool down the helium atoms to extremely low temperatures, like minus 270 degrees below zero. And then the antiproton particles come down that beamline there. Two of my colleagues are adjusting that device there. Comes down, and then it enters into this helium target. And there we produce the antimatter, antiprotonic helium atoms, they are called. These half matter, half antimatter particles. Okay? And they stop, in fact, inside this chamber. Maybe, I don't know if you can see, inside this window, the antimatter particles are formed. And then we shoot powerful laser beams from the left and from the right to the antimatter, antiprotonic helium atom. And then when these lasers are precisely on resonance with the atom, we can make them, we can resonate these antimatter particles and thereby measuring the transition frequencies. In fact, we have a very large apparatus on the other side of this hall where there's many lasers are present.
And then, so could you explain why it is important to measure the weight of the antiproton? And what is the result? You say that antiproton is the same than protons?
Mm-hmm. we know that from the result of this measurement, we have determined that the antimatter, the antiproton mass relative to the electron mass, we've measured to a precision of 9 digits. And we found that the antimatter, the antiproton mass is exactly the same as the proton mass, so therefore 9 digits of precision. And this is important because we believe that the universe.
So now that we know that antiproton is the same mass as proton. So what is the conclusion? You can say that.
Well, we can only say that our understanding of particle physics, which is based on our belief that the two particles should be the same, has been confirmed to 9 digits. But it does not exclude that maybe at the 10th digit or the 11th digit, as humans, how to say, technology advances, we can probe deeper and deeper and to higher and higher precision whether the two are the same or not. And of course, we've always liked to go to the highest possible precision because we don't know whether maybe at the next level of precision these things can be broken or not. They are actually working. So that is my colleague Anna Shota and Todoroki Kenichi. One is from University of Tokyo, the other one from Max Planck Institute for Quantum Optics. And yeah, so, well, what? So they are. Why don't you continue working?
No, just continue.
I have nothing to discuss with you.
Ask how the work is going.
Yeah. Wow.
Oh, how the work is going.
Maybe I can pretend to also work.
You pretend you can.
Yeah. I really look like a bureaucrat who has nothing to do, right? This is not so very nice.
So you know, you're now upset that my street system isn't.
That is not a very good spectacle.
You know where they are?
I don't know. He's filming you. As you work on your software. So this is the peak corresponding to the signals from the antiprotonic helium atoms. She requested. I could turn it on if you want.